Yeah. Ready to go now. Ready to go. So, pull everything up here in the proper layered order. It looks like we're on. Okay, today is our last content lecture day. Outstanding. It's unbelievable to think that the end of the semester has reached us so quickly. We've got one more lecture next week that's going to go through a final exam review, but this lecture is the last time we give you new material. We'll be talking about Knapsack Problem, and we're going to solve it a bunch of different ways using quite a few of our different algorithm families. And then we'll also talk about a couple of shortest path algorithms, which we've alluded to in the past, and that is, of course, Dijkstra's algorithm. And we won't get into it, but then Floyd's algorithm is also included in the slides. Floyd's is another way to do all points shortest path. Okay, so on the front here, we've got our last XKCD possibly of the semester, at least our last one for content. And this is got some knapsack in it. I talked about how the XKCD comic is really smart and really funny. And we got some people at a restaurant. We've got a menu here, and the patron asks for exactly $15.05 worth of appetizers, and the waiter, of course, is not feeling that exactly. And so here you can use the knapsack problem to figure this out, to bring us exactly $15.05 worth of appetizers. And then the waiter says, well, I've got all these other tables, I can't be spending time on this. Well, if you need some help with that, I also have a good way for you to read up on the traveling salesperson, because that will get you to all of your tables faster. So these got to be the worst kind of patrons to have at your table as a waiter, I would think. But they're all a bunch of computer programming nerds like myself, I'd imagine. All the patrons are. So, all right, there we go. Let's look at what the knapsack problem is in general. We'll discuss it, define it, and then we'll break into the 4 different ways that we start looking at trying to solve it. The simplest way to discuss the knapsack problem is we've got a thief that's robbing a safe. In that safe, there are some items. We'll use the letter N here to represent the number of items in the safe. And each of the items has some physical constraint and some value constraint. So it's worth something, and then it either has a size in terms of volume because the bag is measured in volume, or it has a weight because the bag is measured in weight. It's a little dodgy there when you think that this bag could be an infinite size as long as it doesn't hold more than M pounds, or it could be the other way around where it's got some minimal size no matter how much weight you put in there. But this whole thing with the knapsack and the breaking into the safe and the heist movie comes to mind, and stealing, it's just a fun way to look at this problem, when in reality this type of optimization is vital to so many things. Whenever you've got some sort of resource constraint and some value that you're trying to optimize, a knapsack problem solution would be appropriate. So if you're thinking about maybe going out to do a fantasy football team, and in this fantasy football team you've got a salary cap, and there's only so much money that you can spend, that's your physical constraint. Then if you look at how each one of the players is expected to perform, you say, well, I'm going to get this much performance for that much money, and I've got some constrained amount of money, and that is a quintessential knapsack problem. So if you're hiring salaries for your company, if you've got, right now I'm in the middle of doing an addition on my house, and so there's some minimal amount of money, and every time we decide to add some feature, we got to figure out which features we're going to cut out or where we're going to get the money from to do that. And that's a knapsack problem. If you're packing up a truck to go and ship some things, there's only so many things that fit in the truck of that size. How many items are going to get delivered? That's kind of a knapsack problem right there. So the problem is to find the maximum value in the knapsack problem is to find the maximum value the thief can pack into the knapsack that doesn't exceed its capacity M. You don't want the thief walking down the street with stolen merchandise hanging out of the bag. Sorry with the nose is running today here. I did get that second vaccination. Now I feel just nose won't stop, headache, sore, saggy. So my last chance to lecture, so I thought I'd get up and do my bit. So sorry for the runny nose thing. Assume the knapsack has a capacity 11. This is M, and there's these 5 different items. There's N. Here is an example set of items. So let's just try to figure out, because it's such a small example, what the optimal would be. With these 5 items of size 1, 2, 5, 6, and 7, values 1, 6, 18, 22, and 28, what's the maximum value I can get in a bag of size 11? It appears that that 3 item and the 4 item with sizes 5 and 6 actually adds up to exactly 11, which is great. But their value is, of course, 40. With the 18 from the 3 item and the 22 from the 4 item, you add those 2 and you get a 40. So as we look through these different solutions, we're going to keep using this set of data. And different data is going to give different results, obviously, in different algorithms. But for the examples we're looking at today, we're going to use this particular set of data. And anytime we see something that isn't 40, we know that we've gotten something that's less than optimal. There are some variations on the knapsack. The general version of it we called the 0-1 knapsack problem. That's where each item is unique, called the sort of the standard version of this problem, where each item is unique, and the 0-1 represents 0 means we didn't include it. It's like just binary. It's like Boolean. So 0 means that item is not included, and a 1 means the item is included. So that's our fundamental basic version of the knapsack problem. Another way we can do it is where there's more than one of each item. So there's some sort of finite amount of each item. There's some explicit list of items. So this ends up being a lot more like the 0-1 knapsack problem. It's just that there's multiple values, or there's multiple items with the same size and value, because there's a finite list of them. Another version of the problem goes even farther to say, well, of all the items, there's an infinite number of each of them. So you can do multiple copies of the same item to figure out what's going to get you the most value in there. But this is when the problem is being formulated and asked. It's not so much about what you have to think about when you're coming up with a solution. The fractional amount. Now, fractional knapsack means if I've got an item that doesn't fit, well, what if I cut it and make just the amount that fits go into the bag? Now, for instance, if you've got a bag and you're stealing artwork and you steal a painting, and the painting doesn't fit in the bag, and you decide to cut the painting in half, it's not going to be worth as much as it was before you cut it, and more than likely it's not going to be worth half as much. If you cut it in half, you still won't get half the value. So it's not always reasonable that fractional would work. But if we're talking about gold bars, I say half a gold bar is worth half of a full gold bar. So if only half fits and I can if I can cut the thing and put it in there, what remains, then I'm going to get that value. So different problems allow different ways to get to the solution here, and fractional knapsack is one there. Another way that it can be often formulated is we can use weight instead of size. So as I mentioned before, when we're talking a size version of the knapsack, we don't worry about weight at all. So really this bag could hold an infinite amount of weight as long as the size doesn't go over that M. The other version of this where we use weight instead of size, now we say that it's got an infinite size as long as it doesn't weigh more than X. And so this is sort of a simplification of the way that reality works, but we often do that in engineering problems when we sort of constrain a particular value and just work on what really matters. So these are just variations on the knapsack theme. we will mostly be talking about the 0-1 knapsack version. There's the algorithm families we already discussed, brute force and greedy, that were a good pair, divide and conquer and dynamic programming, and then backtracking and branch and bound. So those are my options, but let's break those down. Brute force, sure, that's going to get all the solutions. We're definitely going to find the best way there. Greedy, we can see how that can get us to a solution. It might be a good one, it might not be. Divide and conquer doesn't make a whole lot of sense. So if I'm trying to find the best way to fill a bag of size 11, knowing the best way to fill a bag of size 5.5 might not necessarily get me there. I might have items that are bigger than 5.5 that would never fit inside a bag of 5.5, and so I wouldn't include them. It could be the best item to take, but because I was dividing, it wouldn't work. So we're not going to do divide and conquer. DP, that's great for optimization. That's definitely included. Backtracking, that's a constraint satisfaction problem, which means, is there a way that I can put things in this bag without filling the bag too high? There's plenty of ways. So backtracking is going to find a ton of those, but backtracking isn't good for optimization, and since this is an optimization problem, we're going to skip that one as well. So we will do branch and bound. Branch and bound is an optimizer. So that leaves us with brute force, greedy, DP, and B&B. We'll go into those one at a time, starting now. Brute force. As you can imagine, we're going to get to the right answer because we're going to get all the answers. We'll do this by generating all the possible solutions, and with my 0-1 knapsack, these things are either in or out. There's n items. All the possible subsets would be how many items I have raised to the 2 power, right? So if I've got 5 items, then there's 5 to the 2nd power because each item is either in or out. Those are my 2 choices. And then I make those 2 choices for the first item. That gives me 2 ways to do it. When I go for the second item, there's 2 more ways to do that. It's either in or it's out. And so I end up with this thing that goes n to the 2 for brute force. We'll consider all the possible subsets. We'll filter out the feasible solutions. These are the ones that don't overflow the bag. They may be way less than the bag fill, but they won't be more than the bag fill, and that's the constraint violation that we can't have. And then we will find, of those feasible solutions, when we apply our objective function, we'll find the maximum value feasible solution. All right, so here is what it looks like to do all the 0-1s. This is the brute force approach. Brute force approach would look at all 32 different combinations of these 5 items. The very first one here, which is include absolutely nothing, to the one on the far side at the bottom there, which is include absolutely everything. But the 0-1s represent including that item, 1, 2, 3, 4, 5, and then the value shows what they total up to. Things that show up here are what happens when the bag is overfilled. That's all of the red rows here. So it's these last 3 in the first column, and then that last 12 over there in the second column. All of those bag weights total more than M. They're more than 11 if I take those sizes and put them together. Then the gray and green stuff shows me things that do fit, and it is possible to have more than one optimal way to fill this bag. Not with this data set, but with data sets in general, there's multiple ways. There could be the possibility of multiple ways of solving this. So I'm going to say all of my gray and green rows are ways that fill the bag without violating the constraint. And filling the bag is loose there because it might not be full up to 11, but it won't be over 11. So these are ways to occupy the bag. And we see here this green one, which is our optimal solution. That's the one we calculated earlier, has items 3 and 4 in it for a total weight of 40. It just happens to total 11. It doesn't necessarily have to total 11 to give us our optimal weight, though. Be aware of that. This is a brute force pseudocode. We've got this controlling for loop. It goes from I equal to 1 to 2 to the n. So that's all of the power set. And if you'll remember, the power set for math is the set of all subsets of a set. So that's what this generate next power in line 4 is doing, is generating the next item from the power set, which is the next subset of the overall set. So we'll set that equal to some possible set. Then we'll call set size to find the size of that possible set. And we'll call set value to see what the value of that possible set is. And then if set size is less than or equal to m, if set size fits in the bag and the value of that set is greater than what we've already done, then we're going to say this is our new best set. So we set best set equal to possible set, do a copy there, and set the maximum value to that set value. And in the end, we return our max value. So this is brute force. The pseudocode for it is really simple. As long as you can find some way to generate the next power set, that's probably the most complicated thing going on here in this brute force version. And that's the part we're going to wave our hands at and thank pseudocode for not having to write everything. Hopefully you get it. In terms of efficiency, we know that these 2 to the n subsets all have to be evaluated. So we've got 2 to the n times we're going to do something, and each time we've got a new set, we've got to figure out what that set size is. And we have to look through all the items in that set, which in the worst case could be all n items. So checking to see if the set size is less than m or greater than m, so we can discard them, costs us big O of n. We can also figure out what the value is in that same loop if you wanted to, but it's going to cost you a big O of n as well, because you have to look at possibly all n of those items being included and summing up their values to get the max value. So then I end up with my total brute force efficiency as the work I have to do on each subset, big O of n, times the total number of subsets, 2 to the n. So my brute force efficiency is big O of n times 2 to the n. Really slow. You don't want to spend a whole lot of time cracking a safe and figuring this out with brute force, because you would test a lot of things. There's more than 10 items in the safe. You're looking at thousands of combinations here. That's knapsack brute force. How about greedy? Remembering what our greedy family was? Our greedy family said, let's take a locally optimal solution. Let's do the best thing that I can do right now. And what does that bring to mind? Well, I'm going to take the most expensive item. That sounds great. That's pretty greedy. That's one way to think about it if I think about it in value. Another way to think about it is like, well, maybe I'm trying to fit as many items in there as possible, so I'm going to take the smallest item. That's another greedy approach. Greedy. We could steal the highest value item first. That might not give me the best solution. Remember, we've got our optimal substructure. If I take this greedy first choice and it prevents me from taking some other things, then I might not get a globally optimal solution. And you can sort of think your way through that. If I've got one big item that takes up 90% of the bag and maybe is worth 100. What if I had 2 smaller items that both fit but were worth 60 each? If I were to put the 2 of them in there together, it would be worth 120 versus the one item that's only worth 100, even if they took up the same amount of space. And greedy, when it's trying to find the highest value item first, goes for that highest value item regardless of size. As long as it fits, it takes it. We see that might not work. An alternate way to get there is to say, okay, well, I don't want these big items clogging up my bag. I'm going to put the small items in there. So if I put small items in there first, I'm more likely to get a lot more items in there. Maybe that's going to give me some more value too. But that's got sort of the reverse problem as well. If these small items are all cheap, then I fill up my bag with a bunch of cheap stuff, and I don't get an optimal solution there. If you're really smart, you may say, well, let's just go with value density then. I'll find the highest value density per item, and then I'll stick those things in there. So I'll take their size versus their value and say, I want the item that has the size versus value that's most optimal. I get a collection of those. Is that going to work for me? Sometimes, sometimes not. Might not work if my large items have a high value density, because my large items fill the bag sooner, and then I can't put more items in there, even if they are of a lesser value density. If I can get more of them in there, then I could get a better fill there. So it looks like these three greedy approaches won't exactly work. So here's a chance to look at those. Here's our data set here with these 5 items. Sizes 1, 2, 5, 6, and 7. Values 1, 6, 18, 22, and 28. And then below that, we actually have the ratio. This is a size to value ratio there, or value to size. So we've got ratios 1, 3, 3.6, 3.67, and 4. So if I go by value first, I'll start in the second row, and these things are all sorted already. So to go from value first, I take the item that was worth the most. That's that item 5 of size 7, value 28. I throw that in the bag. Now I've got room for 4 more. So that means I can't have item 4, that's too big. Can't have item 3, that's too big. I can fit item 2 in there. That uses up 2 of my remaining 4 slots. And then I can put one more item, that size 1 item in there. So I end up with a bag that has 35 value in it and only 10 of 11 capacity filled. That's not the important part. The important part is the value though. So this one doesn't end up giving me the optimal solution because I was greedy and I took the most expensive one first, and it ended up preventing me from getting less expensive items but more of them. So okay, well, let's go by size, and we'll start at the bottom here. So in this first row, we start with a small size. I take the 1 item, and then I take the 2 item, that gives me size 3. Then I take the 3 item, that gives me size 8 and a value of 25, but nothing else fits. So once I've put 8 items or sizes, 8 items worth of size, 8 size worth of items in there, now I can't do anything else with the remaining 3 slots because the last 2 items I have are size 6 and size 7, so they don't fit. Either of these are not going to be optimal. If we take the value ratio here, it just looks like we're going in the reverse as we had done value as well. So if we take the ratio 4, which is the highest value density item, it still has a size 7. It uses up most of my bag. I can't fit the next most dense value item, 3.67. I can't fit the next one after that, the 3.6. I can fit the 3 after that, which is the 2 item that has 2 more size. And once again, I'm back to the same thing that I got with value. So this is a way that lets us evaluate all 3 of these greedy approaches and not get an optimal solution. And that's just this data set, mind you. Different data sets might give us globally optimal solutions with different approaches. One particular data set, when you sort the items by size, may give you an optimal solution. Another data set, when you sort the items by value, may give you an optimal solution. But the point is, the greedy algorithm is not guaranteed to give you an optimal solution. Here's a pseudocode version of that greedy algorithm. We've got to first build these ratios, and this is the one that does it by value density. So it builds the ratios by dividing the value by size, and then sorts all of the ratios so that we can look from the most expensive density item first. And then it works our way through these sorted things to see if the thing fits, then put it in there, take away from the total size available, and add to the total value contained. In the end, we return max value. So this is greedy pseudocode. It is quite obviously the hard part about it, not the hard part, I guess. The work that we think of doing, most of the work here is this loop in line 5 to 8, and that's linear, just goes from 1 to n. So that would be linear. However, in line 4, hidden there with one single call, we're doing some sorting, and we know that we can't do a sort faster than n log n. So this then ends up being an n log n for my sort, plus just linear work once they're sorted. So n log n plus n ends up being a big O of n log n. So greedy is much more efficient. Remember our brute force was n times 2 to the n. This is now n log n, much faster, but no longer guaranteed to give me the optimal value. Might keep me out of jail if I'm sitting there at the safe and I get those things in there and get out. That's good. You have to hit a lot more safes. It's worth noting, however, that with fractional knapsack, remember this is where we can take an item and cut it in half and get exactly half of its worth, or cut off 3/4 of it and get 3/4 of its worth. If we've got fractional knapsack, then greedy will give you an optimal solution. Because now we can take the richest item, the highest value density item, put that in the bag, then I can take the next highest density value item. If it fits, I put it in the bag and keep going. But if it doesn't, I cut off just enough to fill the bag. So you can think of maybe a bunch of gold and silver bars, right? You fill all the way up with all the gold bars that you can, and then if there's some more space, you put some silver bars in there, and when you get to the point where you've got just a little bit more space, you chop off a little bit of silver and fill the rest of the bag. That's an optimal solution. So there's knapsack with a greedy approach. Those two were pretty straightforward. Let's look at DP now. If anything, this will not be as straightforward. It works. Dynamic programming is a great way to optimize. And we've got a couple of different things that we do with dynamic programming. In the DP lecture that we had previously, the examples we looked at were enumerations. This is where we're doing some amount of counting with dynamic programming. So we looked at Fibonacci and binomial coefficient and the night moves. Those were all telling us, give me some number. I didn't have any maximization or minimization. We were just trying to solve a constraint and see how many different ways can I solve that constraint. When we get into optimization with DP, now we can see things like the knapsack problem, because we do have to keep ourselves within the constraint of filling the bag, or not overfilling the bag, and we want to get an optimum value there. Other DP optimizations are longest increasing subsequence. That's one you should go look up. It's a classic DP solution. Having an understanding of it is good. Another one is the weighted independent subset. Go look those up. There's various ways that those problems get formulated and turned around and asked in different questions. And once you've understood a few of the good DP solutions, you can often just repurpose an older solution and use that for a new problem. Both of these can be solved top down or bottom up, but we'll see how often our optimizations are going to favor the bottom up, because we can start with the small values and it's easy to think of them that way. It doesn't favor it in terms of being a better way to code it. It's just often easier to come up with a solution from the bottom up when you're doing an optimization. It's easier to think of, well, how do I optimize a smaller bag? You know, if I'm trying to get the best 11 bag, if I've got the best 10 bag, that should be pretty easy. But if I'm going to get the best 10 bag, maybe if I get the best 9 bag, that will make that easy. And so that's how we're going to approach this one here with DP. So in our DP knapsack, we're going to have two thieves now. The master thief, who doesn't want to get thrown in jail, so sends the apprentice thief off to the job. Sends the apprentice thief with everything the apprentice thief needs. The alarm code, the safe combination, and of course the knapsack. In addition to that, there's a list of items that are going to be in the safe and this wonderful table that tells the thief, the apprentice thief, exactly which items should be in there depending on the size of the bag. So this is how our computer science aware master thief was able to get this DP solution in there. So that's where this table comes from. Now, when the apprentice thief gets on site, there's one extra item in the safe. How does the apprentice thief handle it? We're going to take that item or leave it. If we already knew what we were going to put into the bag, then trying to add a new item has a question, well, the bag was going to be full or full enough, if we've got one more item, do we include it or don't we? Do we take some things out to make it fit? So that's the trick here. And often when you're doing DP problems here, it's a good way to think your way from the end back to the beginning. Even if you write this from the bottom up, you say from the end back to the beginning, and from the end back to the beginning is like, well, I've got one more item. Should I include that item or shouldn't I? So the best way to solve this is either to not include this item, because I already had the optimal solution before that. So I either don't include the item, or I figure out a way to include the item. That's what this approach is going to do here. So as we do this, each item is either going to be taken or left behind. If it's too large, obviously it's left behind. If we can make enough room to include it, it will be included, but only if it's worth our while. So if taking some things out to fit this in there ends up losing value for me, then I won't take things out to fit it in there. So in bottom up, we will use these two nested loops. We'll look at our items one at a time, the first item, and we'll see which bags it fits in. And then we'll add the second item and see which bags it fits in and improves the haul with. And then we go to the third item and see which bags that fits in and where it improves the haul, and so on. We're going to build and use this 2D memo, and we're going to go from our 0 items all the way to the n items. And as I'm looking at each one of those n items, I'm going to look at bags that go from size 0 all the way up to m. All right. Here is an actual C++ implementation of a knapsack DP. We've got 4 loops in line 6 and 7. The for loop in line 6 goes from 0 up to n. The for loop in line 7, which is nested, goes from, the worst case, 0 up to m plus 1. So that's a big O of n surrounding a big O of m. So it's easy to figure out then that this is a runtime, a big O of mn. All right, I've got a memo here declared in lines 3 and 4. And it's important to note that we are programming in both of those directions, whether or not I'm going to include the items and whether or not it fits in the bag there. So I've got this memo of size n plus 1 by m plus 1. I'm going to fill that with a bunch of zeros, so then later on I can see if there's anytime there's a value, I've already calculated it, and I can just use that. M is the total size of my bag. Right? M is the total size of my bag, n is the total number of items. So in line 8 and 9, I'm looking at a particular bag size, right? If j, and j is this iterator that goes from 0 to m, so j is a bag size iterator. So if the size of the bag is less than the current item's size, what does that mean? It doesn't fit, right? If the size of the bag is less than the current item size, then that item doesn't get included. Full stop. It just doesn't fit. So then what I can say is the memo at that position then is as if that item didn't exist. So our rows here, our I iterators, those are whether or not this item is included. Is the first item included? Is the second item included? Is the third item included? If the fourth item doesn't fit at a particular size, so say I'm trying to include this fourth item in a bag of size 8. If the fourth item doesn't fit in a bag of size 8, then the best bag of size 8 I can have is exactly the bag of size 8 with just the first 3 items. So that's where in line 9 it says if j is less than this item's size, then at this location just write the value directly above this there, right? Write the value from this size bag without this newest item. So that's what the I plus 1 is. That's this newest item, and the I is without this newest item. So If the item doesn't fit, then obviously we're just going to take the value of this bag as we already have done it. If it does fit, then we've got a chance to see how am I going to put this in there. The real simple version is when I've got a bag of size 9 and then I go up to a bag of size 10, if I've got an item of size 1, then obviously I could just drop that in there because the bag of size 9 is optimal and the one size item fits inside a bag of size 10. Great. But that's not all of the items. What if the item I'm looking at isn't size 1? So now I'm looking at having already solved the bag 9 problem. I already have an optimal solution to a bag of size 9. If I'm trying to add an item of size 5, I obviously can't just pile it on top of the best 9 bag to get a 10 bag. What can I do with an item of size 5 to get to a better 10 bag? Well, if I was to take that item of size 5 and combine it with the best 5 bag, if that makes a better 10 than just using the old 9 bag without the new item, that's when I take the item. That's when I make room to add this thing in there. If throwing something out of a smaller bag and putting this in there works, that's when I take it. So that's what this algorithm does here. And in line 11, it says we're going to set this new value by taking the max of the previous set of items in this size bag, because that means we haven't added anything to the previous one. Let's just take, we have to beat that. And the max of that plus, let's move over and see how we can get this new item to fit. If I can find a way to make this new item fit, then I can see, well, if it's good to take it, I will. And so that's what the max does there. It says look at not including this item versus including this item in any way we can make it fit. All right, let's walk through this here. So I've got this 2D memo now. It goes from 0 to 11 across and 0 to 5 down because I've got these 5 items and I've got this knapsack of size 11. And I'm just going to work on this in a nested loop form. I'm going to go across in row 0. I'm going to go across in row 1. I'm going to go across in row 2. And that's going to represent what happens when I include 0 items. Well, that's pretty obvious. If I've got 0 items included, I'm hoping that I got 0 value in all of these bags. That's good. So that one went pretty quick. How about if I include this first item? Well, the first item is size 1. So if I try to put that item of size 1 into a bag of size 0, it's not going to work. So I don't put it in there, which leaves me a bag of size 0 with a value of 0. Not impressive. Didn't take scientists to figure that one out. But when I move to the next position, I see that now I've got one size in my bag, and I can fit this one size item in there, and it's also going to give me a value of 1. So there I put the 1 in there. As I get to the next item, of course, sorry, it's not the next item, it's still the same item. I'm still trying to see, well, what's the best way to make a bag of size 2 with or without this number 1 item? Well, it fits, so I'm taking it. Same thing with 3. It fits in a bag of size 3, so I'm taking it. It fits in a bag of size 4. It ends up fitting all the way across here, which makes sense. That one size item fits in any bag from size 1 to 11, and it contributes 1 value. That's it. Next row. Of course, the 2 item has a size 2, so it doesn't fit in a bag of size 0, so we just take the previous version of that. We actually just look up to this previous row, and since the 2 item doesn't fit in the bag of size 0, we copy the value from right above it down. Same thing here as we move to this second column. Now we're looking at a bag of size 1, which the number 2 item, size 2, doesn't fit in. So we just look at the previous bag and just bring that score down there. That's where the 1 comes from. At our first bag of size 2 now, this number 2 item finally fits. its size is 2, its value is 6, which is better than the 1 directly above it, so we take the 6. After that, it looks like this fits, right? So here we are trying to determine what to do with this number 2 item in a bag of size 3. In the algorithm, we said, if it doesn't fit, then obviously we don't include it. But if it does fit, let's see if we can make room to fit it in there. And since the 2 item has size 2, as we try to fit that into a bag of size 3, what we really want to do is say, well, I could fill this bag of size 3 by including a 2 item, and then also I could throw the best bag of size 1 in there, because the 2 item has size 2, and obviously the best bag of size 1 has size 1, so that gives me a size 3. So if I can say include all of those things, then it works, right? So then I do include it. The same thing goes as I go across there. It's not going to get any more once I keep adding this 2 item to these other larger bags. Once it fits inside the 3 bag along with the 1 item, it also fits inside the 4 bag, the 5 bag, the 6 bag, the 7 bag, the 8 bag, 9 bag, all the way to the 11 bags. So we've done that. Next up, the 3 item. Obviously it doesn't fit into a bag of size 0. Doesn't fit into a bag of size 1, so we just copy the value from directly above this. The best way to get a bag of size 1 including the number 3 item is to not include the number 3 item. It doesn't fit. The number 3 item is size 5. Same thing here as I go to the number 2 bag, or sorry, the size 2 bag, the number 3 item doesn't fit because the 3 item is size 5. It doesn't fit in the 3 bag, it doesn't fit in the 4 bag, but the 3 item does fit in the 5 bag. And we can see here that the 3 items 5 bag score, we're going to combine that with some other location in the memo. We're always trying to look something up in the memo because we realize that everything that's filled out in our memo above where we're working is optimal. So I'm trying to take an optimal combination and see if that beats not adding the thing. So not adding the thing in this position here represents bringing that 7 from row 2 straight down. So at 2, 5, we've got a 7. So the question is, can I beat that 7 by including this number 3 item? And I can do that by saying, well, obviously it's got a size 5 and a value of 18. But what do I add that to that's in my memo already to figure out if it's worth doing? Well, I'm at that size 5 and I'm trying to put in a size 5 item. So the best way to do that, if I've got a bag of size 5, if I put this size 5 item in there and my best bag 0, well, bag 0's all cost me 0. That's pretty simple. But as we move over one, how about this 6 bag? So the best way to fill a 6 bag with this 5 size item is to include the 5 size item and the best 1 bag. Those things fit into a 6 bag. A best 1 bag and a best 5 and this 5 item, that's a size 6. And so that's where we get that from. We take the 18 of value from this number 3 item and we add it to this 3 item row bag 1 size. It's got the value 1 there. So that 1 plus the 18 is the 19. And if that 19 is better than just copying the 7 straight down, we take the 19. And that's what we've got. As we move across, we see we'll do some more of the same. What happens now when I try to put this number 3 item in a bag size 7? Well, the best size 7 bag that includes this size 5 item would be to put the size 5 item in there with the absolute best the best bag 2. So if I put those together, the best bag 2 here has got value 6 plus the value 18 from the number 3 item. That's 24. And then the question is, well, does 24 beat 7 from the row above it? Obviously it does, so we're going to include that. So that 24 gets included, and then we've got more work as we go across here. So every time we're looking in our memo in the same row minus our size. So as I'm working on the number 3 item with size 5, I'm going to look in this 3 row from where I'm working and subtract that size. So that 8 came from subtracting 5, which is the 3 column in the 3 row, which has a value 7, and I add the 18 to it. If the 25 is an improvement over the 7, then I do it. If it's not an improvement, I don't do it. So we finish those all the way out, because now once we get to that position in the bag 8 with items 1, 2, and 3, that actually has all 3 of them in there. So it doesn't, we never get more by going into larger bags. We just keeping the same 3 items. So hopefully this is making some sense out of it. The next one shows up. Obviously, as we're looking at the number 4 item, it's not going to fit in a 0 bag. The number 4 item has a 6 size, so we don't expect anything to change until that thing fits. All we do is keep writing things down from directly above. Before it fits, we just take from the row above. So in bags 0 through 5, since this number 4 item of size 6 doesn't fit, we just copy from the row above. Once it does fit, then we look back in this current row some number of columns and see if we can get a better value for it. So in this next one, we're looking at trying to put this number 4 item into a bag of size 6. Well, the number 4 item is a size 6 item, and it's got a value of 22. So if I want to fill an optimal bag 6, it could be including this 6 size item and the best 0 bag, or it could be just using a 6 bag that I already had somewhere back up above it. And so the best 6 bag up above it is the row right directly above it, and that was including this number 3 item for a total value of 19. But since the number 4 item is worth 22 all by itself, we say that's better than taking from the row above. We're just going to include that item. As we move across, we'll see that here we decide not to take that item. And this is not as clear unless you pay attention to the numbers, right? So to see in the 4 item bag of size 7, should we include the 4 item? Well, if we were to include the 4 item in a bag of size 7, that would be taking the best 1 size bag, which is going to be 1, and putting this 6 size item in there for a total of 23. 23, however, is not an improvement over the 7 bag that I had that didn't include the number 4 item, so I don't include the number 4 item. That's why the 24 is written from directly above that in column 7, row 3. Now it fits and it makes a difference, so we're going to include that. So at bag of size 8, I would take that 6 size item plus my best size 2 bag. Best size 2 bag is 6. The 6 size item is 22. Total 28. 28 is an improvement over 25, so we do it. Right? And we get down there to finding our optimal at the end. We don't know it's our optimal yet, but we have included this, and we know, since we're working on this particular example, anytime we see that 40, we've actually got the right answer. But where did that 40 come from? Right? That's that 11 size bag with the number 4 item, size 6, value 22. We just go back to the best bag of size 5 in this row, which has got a value 18. We add the 18 and the 22, that gives us 40, so we have included that value. We work our way across the bottom row. This one has got a size 7, so 0, 1, 2, 3, 4, 5, and 6. We don't make any changes at all. We just copy the number from the row above, because we can't even include that item until we've got at least 7 space. 7 space makes sense to use that rather than the bag above, because the bag above, having not included the 5th item, had a value of 24. Now if we just put the 5th item in there all by itself, it's got a value of 28. We take that, it's an improvement. I can get a 29 by putting the 28 item along with the best bag of size 1, 34, 35. But as I try to get something more in there, you see that this 28 has to be added to my best bag of size 4. My best bag of size 4 is worth 7. So that 7 item plus a 4 bag to fit in an 11 bag makes a value of 35, which is not better. So that's why we do not include the 5th item. We just take that value from the row above. So this then fills out our memo. When we want to know what our answer is, at the end, we just do memo square brackets m square brackets n, and that gives us 40. That's the answer. We see it there. It's 40. All right. Oftentimes, just knowing we've got the value is good enough. Many times we're just asked, what's the best value you can get out of this? Sometimes, however, we say, well, I want to know what the best value is, and I want you to tell me which items are included, because I really wanted to ship these things. So now I don't want to just know what fits. I don't want to know what should fit. I want to know which items actually do fit. So we have to reconstruct the solution, and we can do that by sort of back tracing through our memo. So it looks like any item that we included will improve a smaller solution. Anything that gets excluded does not improve a smaller solution. And what that translates to directly is, as I move down my rows in the memo, if the value directly above this cell hasn't changed, then the item didn't get included at that size. So if a smaller solution plus an item is greater than or equal to the full solution, without the item, it is included, otherwise we exclude it. We can take this completed memo and work backwards from NM to 0 and get there. So this is what the reconstruction will do here. We've got a for loop that is going to run us through each of our N items. And we don't have to loop through all of our M bag sizes, because now we're taking jumps based on the size of the item. So we've just got one for loop here, and we end up filling a vector of booleans of size n that has the thing in or not in. So this runtime is big O of n. You see that we start at our n-1 and start working our way backward from the solution. With this being our completed memo, we see that, well, what's going on at this 40 here? Well, the 40, if we included the number 5 item, would mean that its 28 improved a previous solution. So if we jump back to 4, because that number 5 item is size 7, we jump back to 4 in this row, we see its value is 7, and that 7 plus 28 is not the 40 that we're looking at. So the 40 didn't come from adding the 28 item. The 40 must have come from the item above, the row above, which means that the number 5 item is not included in our optimal solution. Okay, how about trying to determine whether the number 4 item was included in our optimal solution? Now we're at that second box of 40 in the for row, and we say, if we're going back, if that number 4 item of value 22 of size 6 helped contribute to this 40, then we include it. And so if we look back by jumping over 6 rows or 6 columns to the 5 bag in this number 4 row, the 5 bag has an 18, and the 18 plus 22 is equal to the 40 on the far end. So yes, it was included. And so that's where we jump across. The way that we got to the 4 item was to take that previous row's value and put it in there. All right? Same thing here. As I jump backwards, I can see that the number 3 item was included because its value 18 was an improvement over this 0 column. That 18 plus 0 got us the 18, so it was a contributing factor to the solution at that point. So we can then, in that case, we don't have to work our way back any farther, but we can determine that none of those other items were there. That's DP there's a few pieces of code that were included with the slide. I strongly recommend reading them closely, typing them in, stepping through them if you like, or just putting enough print debugging in them so that you got an idea of how that works. Print out various memos, try some different data sets, see how it finds that, maybe make the data sets be a little bit less sorted. But you want to make sure that you get the understanding of why DP works here, because it does give us an optimal 0-1 solution. All right, branch and bound. We won't spend too much time on this because you are branch and bounding in Project 4 already. That's what Project 4C is, all about trying to find that TSP with a branch and bound. So in this case, as we look at branch and bound, it's an optimization, of course, but our optimizations take one of two forms. One is a maximization, one is a minimization. So we're minimizing with the TSP. With branch and bound, we're minimizing. In Knapsack, since we're trying to maximize value, we're going to be doing a maximization with branch and bound. So everything is going to be turned completely on its head. Lower bounds turn into upper bounds, and so on. Higher estimates need to be replaced with lower estimates and vice versa. So that's what we've got going on. Since the knapsack problem is an optimization, we can use branch and bound to solve it. Knapsack being a maximization says now we need an initial estimate and my current best solution. Those are lower bounds. Right? And remember what a lower bound means. A lower bound means this is the lowest I'll settle for. So my initial bound, my initial estimate, that's my lower bound. I'm not going to look for anything less than my current lower bound. And that goes for my initial estimate. And then as I'm developing my solution, I'm constantly raising the lower bound. I'm not going to look for anything less than this. I'm not going to look for anything less than this. I raise it, I'm not going to look for anything less than this. And as that lower bound goes up and up and up, when I get done, that's my solution. When I calculate a partial solution, the remainder is an upper bound estimate. So when we were working in the TSP, remember, we were okay with being wrong with our estimate as long as we weren't wrong too long. If we were wrong short, that was okay because it wouldn't think something was a bad idea that actually was. Well, we're maximizing. Let's flip that all the way around. So now my partial solution, all of my estimates have to be long if they're wrong. Why is that? Because if it's long and it's wrong, it's actually going to end up shorter, right? So if it's long and it's wrong and it doesn't improve what I have, then eventually it's going to be actually shorter, so it won't even be as good as that. So if it wasn't good enough when it was long and wrong, then it's not going to be good enough when it's not quite as long and right. So our upper bound here is now what our estimate is. Our estimate has to be no less than actual, whereas when we were minimizing, it had to be no greater than actual. Now it has to be no less than actual. So a promising says anything that has a total weight of items less than n. That's pretty good, straightforward. Our solution is any collection that is promising. That's great. And our lower bound starts with the highest possible underestimate and ends with the maximum value that we get. We can start with a greedy 0-1 knapsack. That's a real quick and easy way to get an estimate, right? We know that the greedy didn't always give us an optimal solution. It never gave us a solution that was beyond optimal though, so that's a great place to start. We can get a nice high lower bound by just taking this quick greedy run through, sort them, and then linear pass. Now, if I can't beat the greedy, then it's just a waste of time. So there's my first lower bound. That's one way to do it. As I look at my upper bound, I'm going to sum the value of all the things that I've included, plus my overestimate now of what can fit in the remaining space. And I want to prune if my upper bound is less than my current lower bound, right? And it turns out that I can actually just use the greedy fractional knapsack, because remember the greedy fractional knapsack was giving us an optimal value. It was never going to give us something shorter than optimal. So that's great. We can use fractional greedy knapsack here to make that happen, and the greedy 01 to give us our initial lower bound. So that's kind of how we pulled it off in project 4C. We got some lower bound from something quick that we did, and then we used something else that we were going to give us, that might give us something that was illegal, but it would never be wrong illegal, right? So we were able to use MSTs, which wouldn't give us a legal Hamiltonian cycle, but it wouldn't be wrong long. Or here, we can use the greedy fractional knapsack, which is going to give us something we couldn't do, but it won't be wrong short, and that's good. We don't need to use permutations either, because it doesn't matter what order we put things in here. We only need to look at combinations. So we don't have to use gen perms to do knapsack here. We can just do it as a loop through each of the items instead of trying to figure out how to permute them. All right, that's knapsack, branch and bound. Like I said, take some time with the code, but my suggestion is try to get done with 4C before you mess around with this code. It's hard enough to understand branch and bound the first time you're dealing with it, but then as you're trying to get in the middle of dealing with a minimization and dealing with a maximization, it's just hard on the brain. So give it a rest, wait till after you've done, and then double check this code. It's good stuff. Up next, we're going to talk about some shortest path algorithms. We've just got a couple of them I think we're looking at. We're going to look at Dijkstra's algorithm, which is a single source shortest path, and then we'll look at some ways to get to all pairs shortest path. So up first, Dijkstra's algorithm. Some shortest path examples might be something on the highway system. You might be trying to find shortest path by distance. You've seen that on your apps. Normally you try to get a point A to point B. You'll have the option of saying, well, this way is shorter, this way takes less time. That's a different version of shortest path. One that might be important is reducing the number of stoplights. If you're helping a delivery service, time where your drivers are sitting at stoplights is less effective. So the way that the delivery schedules work, the delivery maps work for like UPS and Postal Service, they have the fewest number of stoplights possible, and they also optimize by saying it's faster to make a right turn in the US than it is to make a left turn, because you have to cross traffic to make a left turn, whereas you can turn right on red when you take the right turn. So these routes get optimized for having the fewest number of stoplights and the most right turns instead of left turns. Or, and I don't know why Krispy Kreme locations are important here. Whoever wrote this slide back in the day really liked Krispy Kreme. So one of the ways that you cross the country apparently is by stopping at Krispy Kremes all along the way. I don't know how healthy you'll be when you get there, but you will have had a good time. How about airports? Travel time or how much it costs you. Those are a couple of shortest path measurement styles. Other times you're looking at actual distance. You may be looking at the total number of hops or total number of frequent flyer miles. These are all just ways that we can look at applying this problem in real life. So we're looking at a weighted path length. So if we've already got an edge-weighted graph, what we're doing is saying that the weight of an edge, this C from V sub I to V sub j, is the weight of the edge that connects V sub I and V sub j. And a path is a non-empty sequence of vertices that go 0 to 1 to 3 to 2 and so on. So that's my weighted path length. And I can sum all of those things up and just say, let's take all of them together and see what it is. So that's what we're doing as we try to figure this out. So the shortest path problem then says, given all this graph and these two vertices V sub s and V sub d, my start and my destination, find the path that starts at V sub s and ends at V sub d that has the smallest weighted path length. In single source shorted path, we end up actually finding the shortest path from V sub s to all the other vertices. And if you think about why that would be, if I'm trying to figure out the path from one particular vertex to another vertex, I never know which vertexes it has to go through. So unless I find the path from all of those vertices to the end, then I might be missing something that could get me there soonest. sooner, right? So to find the shortest path from V sub s, I'm going to find the shortest path from V sub s to everything, and that will be sure that I found the shortest path from V sub s to V sub d. Sounds like an unbelievable amount of work. Sounds like more work than we need to do, but we can't do it with less work. So here is a graph that's got these 6 points in it, A, B, C, D, E, F, and this one is a directed graph. We can do this with undirected graphs or directed graphs as long as we've got something going on here. So we're looking for a shortest weighted path from B to F. Goes from B to A for 3, A to C for 1, C to E for 4, and then E to F for 1 more. Total weight is 9. That's my shortest weighted path from B to F. If I look for an unweighted path, now the shortest path is one that has fewer edges. Not worried at all about how long those edges are, and so this one has 3 edges only. So it goes from B to C to E to F. So now that ends up with a total path weight, but we don't measure weight when we're talking about unweighted. We're just talking about the total number of edges. So this has got 3 edges, what makes this a shortest unweighted path. Shortest path problems, there's really kind of breaks down if you've got negative cost cycles. So if it's possible in your problem to have a negative cost edge, some problems it is possible, other problems it's not. Obviously, we can't have a map and you say the distance from here to there is -5. But there are some situations where you say, well, this one has a negative resource use, where taking this path costs some amount of money, some other path might actually cost 0 or even have a return value because maybe you're doing something there. So it's possible to have graphs with negative values. And when that happens, then we can't necessarily get this shortest path problem solved here. There's this loop here from A to C to D to A. So A to C is 1, C to D is -8, and then D to A is 5. So with that, I could just take this cycle a few times to make some money, as it were. So I'll spend 1, then I'll get paid 8, then I'll spend 5, and I'll be back at 8. So I'll be back at A with 2 more in my pocket. If I take A to C to D and back to A again, now I'll have 4 in my pocket. So I can keep going around here until I've found a way to make whatever value I wanted. And that's not going to necessarily give me a real answer of what the shortest path is. So in this case, going through to D to A to C to E to F costs 4. D to A to C to E to F, or D to A to C, D to A to C to E to F costs 2. D to A to C, D to A to C, D to A to C, E, F costs 0. So I can make that trip from D to F in various arrangements when I've got negative cost cycles, which is why we can't do Dijkstra's if there's negative values in the graph that we might be taking. Dijkstra's is greedy, if you're trying to figure out which family it's from. It's a greedy algorithm for solving the shortest path problem. It assumes non-negative weights, and it finds the shortest path from V sub s to every other vertex. As we do Dijkstra's algorithm, we've got some things we need to know. We need to know some K sub V, D sub V, and P sub V. That sounds familiar, doesn't it? Well, it should be. This is a lot like Prim's algorithm, and actually Prim's algorithm is often, Prim's algorithm has a ton of names, and one of them actually has Dijkstra included in it. So the Dijkstra's algorithm and Prim's algorithm are very similar. We'll see how it's, there's just one small little step in there that differs between the two of them. So the K sub V is exactly what we used it as in Prim's algorithm. Is the shortest path from V sub s to this particular vertex known? So it's always false when we start, and then we find the shortest paths and we mark them as true when we do. D sub V, what is the length of the shortest path from V sub s to this vertex? Of course, we're going to start out as infinity because we're minimizing, so we're going to take the really long value and see if we can't shorten that up. P sub V is what vertex precedes it or is the parent of. How did this thing get connected on the shortest path from V sub s to here? So initially that's unknown, just like in Prim's. So we'll start out with something that is similar to how we set up prims. Now we've got this graph here, A, B, C, D, E, F, and in this case we've gone undirected, but we've got these 8 edges that connect these 6 points. And what we're going to do is start from our start location. In this case, we're trying to find the shortest paths from B to F, which is really going to give me the shortest path from B to everywhere. So I'll start out by setting B's distance equal to 0. And then just like prim, I've got this loop that goes through there and says, well, find the thing that's marked false that has the shortest value. That's B. And almost exactly like prims here, you see that we've updated the things that B is adjacent to. B is adjacent to A and C, whose previous distances were infinity, but now you see that we've changed that to 3 and 5. But why did we change it from 3 to 5? Well, there's an edge from B to A for 3, and there's an edge from B to C for 5. So that's cheaper than infinity. We connect them, and we say that the parent of A then for this 3 is through B, the parent of C for 5 also through B. So far, it's identical to prims. After this first step, though, is where it changes just a little bit. And it actually changes a little bit in the first step, we just couldn't see it. And how it changes is, when I'm at some position, it's not free to be there. When we're trying to make an MST, we can connect anything from anywhere. That was the whole point. But when we're trying to find the shortest path, you have to pay something to get to a particular location. So our starting location B, we paid 0 to get there, so that's fine. We actually added 0 to the 3 edge, which is why we wrote 3 here with A. We added 0 to the 5 edge, which is why we wrote 5 here with C. Now, as I go through, just like prims with a new outer loop, my outer loop is going to go through all of these, find a false that's got the shortest value. It's going to be A. A has a 3 next to it, which means that it costs me 3 to get to A. So when I update A's neighbors, I don't just add the edge from A to the neighbor, I add the edge from A to the neighbor plus the cost it took me to get to A. So as I look at A's neighbors, A has neighbors B, C, and D. Well, B is already marked as true, so we completely ignore that. C has got an edge from A to C for 1, but since it costs 3 to get to A, it's 3 plus 1 for a total value of 4 to get to C. And that's why we've overwritten the 5 that was previously in C with this 4, because I could have gone from B to C for 5, or I could have gone from B to A to C for 4. And that's what's going on there. And we've updated the parent, of course, there. And the same thing as we update D, we see that it costs 3 to get to A, plus the edge from A to D for 5 more. So the total cost to get to D is 8, which is better than infinity. So we take that and update D's previous as A. So it functions just like prims in that we've got this outer loop. And then the first step in the loop, we find the closest thing that hasn't been determined already. Then the second step, we mark that thing as true. And then there's just a slight difference in the way that we update the neighbors in step 3 of what would have been prim's algorithm to make it Dijkstra's algorithm. In prim's algorithm, we just measure those edges. In Dijkstra's algorithm, we measure the edges and add the cost to get to that root, to that source vertex. So as we go through here, then we end up marking C as true next because it has a distance of 4. It costs 4 to get to C, so C being adjacent to D for 2 means it's 4 plus 2, or a total of 6 to get to D, which is cheaper than we had before, so we take that. And 4 to C plus 4 to E gives a total cost of 8 to E, which is cheaper than infinity, so we'll take that one as well. We work our way through here. We end up filling in each one of these trues. And finally, I end up with this table that looks a lot like prims. When I get done, all my case of V's are true. When I get done, all my piece of V's have how this particular thing was connected. However, when I got done with prims, I could add up this D column and say this is the total weight of my tree. This is no longer a tree anymore. This is a collection of paths. So what I get out of the D column is the total distance from our starting vertex B to that vertex. So the D in the A column says that the total distance from B to A is 3. In the D column for F, there's a 9. It means the total distance from B to F is 9. That's how we read this table. Well, how do we get to F? Well, let's just backtrace on what we had. So if we go from F back to E, E goes back to C, C touches to A goes to B. So that's our path that we would take. That's our shortest path. F to E to C to A to B. F to E to C to A to B, that costs us our 9, and this is how we use Dijkstra's algorithm. If we go back, we can just sort of enumerate those previous's. So here, we've just taken and drawn these backtrace arrows that goes from F to its previous, which was E. It goes from E to its previous, which was C. C was also D's previous. We go there as well. IA's calling during lecture. Fail. All right. So how about the complexity on Dijkstra? Dijkstra is a big old V squared. It's a simple nested loop thing, a lot like prims. Just for every vertex, I'm going to find the min using some linear search. If we had a sparse graph, we could do E log V using a heap. And that would end up being something that looks like a big O of E log V squared, really, because we're looking at each one of the vertices. But since E is on the order of V there, then we can still find the shortest edge in a heap, and we end up with this E log V. Good explanation in the text there, 24.3 at CLRS. So that's Dijkstra's. Here it is in some pseudocode with our complexities attached to it as we create a table here. Obviously, I can get that done fairly cheaply. I figure out n, that's the total number of vertices. I can get that in constant time. Creating my table of size n costs me 1 for each vertex. I need to set the k, d, and p. Then creating an empty heap in constant time. I can set the value of one item equal to 0 in constant time and insert the first item into the priority queue in constant time. Then we just go through this thing where we pop something out of the priority queue, put the things around it into the priority queue. We keep going until nothing comes out of the priority queue. Anytime we pull something out of the priority queue that goes to a place that's already marked as true, we throw it out. All right? So this is the rest of Dijkstra's algorithm here. While the priority queue is not empty, in the worst case, we're going to go through all of the edges there. So that's a big O of E. As I get the min, that's a top and pop. That's a log E because I do pull off the top, which breaks the priority queue. Then we have to fix the heap. That's the log E fix. I can check that to see if it's not known. That's just checking its K. Get it in constant time. Set it to true if I haven't. Then as I look for all of the things adjacent to this current vertex, that's 1 plus E over V, right? We found where that thing is in the table and looked at all of its adjacent vertices. And so this is obviously drawn in the adjacency list method because we would only use the priority queue when we were talking about a sparse graph. So we would have a sparse graph representation, adjacency list. If you wanted to do this with adjacency matrix, then we're talking dense graph. We just do the prims sort of nested loop thing. So the rest of these things go through how this works. There's the inserting into the priority queue. That's a big O of log E in the worst case. And then as we build this edge set and work our way out, we get to our final answer. So that's Dijkstra's algorithm. Puts us right up here at the edge of time. We've got one shot to work through this one. So here's a good graph. And remember, as you're trying to work on this for the exam, this is a great exam problem here. It's pretty simple. If you wanted to just kind of glare at this graph for a couple of minutes, you could figure out what the shortest path from O to T is without using any algorithm other than just sort of adding things up and seeing what works and what doesn't. So then if I was going to ask you a question on the exam about how do I find the shortest path from O to T using Dijkstra's algorithm, obviously asking you the weight of that path would not be a good exam question because you can figure that out without using Dijkstra's. How then could you see to using Dijkstra's? So as you attempt to find the shortest path from O to T on this graph, start out by setting O's distance to 0 and then work your way through Dijkstra's algorithm. Along the line, think of questions that could be made as good multiple choice questions to prove that you understand the steps that are required to do Dijkstra's algorithm. When you get done, like what is the parent of such and such, right? When you get done, how many values have this and that? So this is what you should do as you are sure, you're making sure to yourself that you understand Dijkstra's algorithm. You should work through an example or 2 or 3 and then try to come up with some exam questions of your own. What would be a good way to prove that I know that I did Dijkstra's correctly? This is where we leave off at the all pairs shortest path problem. So here now we're trying to find the shortest way from any place to any other place. That's what the all pairs shortest path problem is. If I want to go from A to B, what's the shortest way to get there? If I want to go from G to K, what's the shortest way to get there? So that's all possible pairs. One way to do this, of course, is to run Dijkstra, starting at every location. So that would be running Dijkstra. So if I had a dense graph, that'd be a V squared running of Dijkstra, plus I would do it once for each vertex, so that's V cubed, which might sound terrible, but actually doesn't get any better. Other ways to do this, rather than running Dijkstra V times, is I could use Floyd algorithms for dense graphs or Johnson's algorithm for sparse graphs. Those are some things that you can look into, but not things that will be covered here in 281. This is where we stop. We have some really good slides on Floyd-Warshall, so have a look at them. It's fun. It's a great algorithm to understand. So Floyd's algorithm, the Floyd-Warshall algorithm, is a DP solution for all pairs shortest path. So the good news about that one is you can get a little bit more practice looking at DP solutions, and you can learn something about all pairs shortest path, but you won't be doing this on the exam. It can be helpful for understanding it, but it works out. It ends up being a big O of V cubed, best, worst, and average case. So not different from calling Dijkstra's V times in the overall complexity, but it's an interesting approach. So check that out, and I think it's about time for lunch. This is me signing off on the content side. I might get a chance to wave at you from the final exam lecture, final exam review lecture given by Dr. P in a couple of days here. But other than that, it's been good. I'll see you in the office hours until we get done with this, and also at the exam. But stay safe and take care. Robin Banks, that's right. I always wanted to be in a heist movie, so let's do that. If anybody wants to do a heist movie, then just call me. We'll set something up.